We were just studying the conceptual discrete random variables, starting from the Bernoulli random variable. Bernoulli random variable is a random variable which can only take two possible values, 1 and 0. So 1 represents a success and 0 represents a failure. And when you perform a random experiment, the outcome of which is either a success or failure, we represent the outcome with a random variable that is Bernoulli distributed. Now, the probability mass function of the Bernoulli random variable is either equal to p or 1 minus p, depending on the random variable is taking the value of 1 or 0. And the p value here is the probability of the trial to be a success. And depending on different values of p, a Bernoulli random variable can be defined differently. So the expected value of a Bernoulli random variable is basically the potential values that it can take weighted with the respective probabilities. Therefore, it is equal to p, and variance of it is equal to p times 1 minus p. Now, by using this concept, the Bernoulli random variable, we can skip to another random variable, which is much more frequently used than the Bernoulli random variable, and it is called the binomial random variable. Let's just assume that we are repeating a Bernoulli experiment which results with a success or failure with respect to probabilities p and 1 minus p. We are repeating this experiment for n independent times. And in these n repetitions of the experiment, we are trying to count the number of successes that we may observe. So the number of successes that we may observe can change between 0 and n. So we can maybe observe no successes, maybe 1, maybe 2, so on and so forth. Maybe all of them will be success. So it depends on the probability p, right? Now, the probability of observing exactly x successes out of these n trials is going to be n choose x times p to the power x times 1 minus p to the power n minus x. And here, in order to define a binomial random variable, we need to determine the number of experiments, the number of repetitions of the Bernoulli experiment, which is n, and that is called the size parameter. And we also need to define the success probability p again. So the binomial random variable is a random variable with two parameters, size parameter and the success probability. Now, the expected value of a binomial random variable is going to be n times p, and that is the proof of that, but we are not going to explain the proof. Logically, if the expected value of a Bernoulli random variable is p, then if you repeat this experiment for n times, then total number of successes that you are going to be observing would be proportional to the probability and the number of repetitions. Therefore, n times p is the logical answer for that expected value. And similarly, the variance can be calculated through the convenient formula of the variance, and that becomes n times p times 1 minus p. Now, actually, a binomial random variable is the sum of n independent Bernoulli random variables, where n is the size parameter. So the variance of a binomial random variable should be equal to the sum of the variance of Bernoulli random variables. Because we have n Bernoulli random variables that are independent from each other, we can say that the variance of a binomial random variable is equal to n times p times 1 minus p. We can continue with an example here. The probability that a patient recover from a delicate heart operation is 0.9. So if you assume that this is a Bernoulli experiment, the success probability of this Bernoulli experiment is 0.9, and we are asking the probability of exactly 5 of the next 7 patients having this operation to survive. Well, actually, we are talking about the binomial random variable here, where the number of independent repetitions of the same experiment is 7, and the success probability is 0.9. And we are looking at the probability of exactly 5 patients to survive. Probability of x being equal to 5 is equal to 7 choose 5, then the success probability to the power 5, and the failure probability to the power 2, and that becomes 0.124. And even though the question does not ask for the expected value and the variance, but still we are calculating them for the sake of completeness of our learnings and of our revision on this part of the